Aim of the talk. So Barry asked me to talk about where I thought transportation was going in terms of power electronics. And I felt, well, I don't know, a bit like Bill. It's like, if I knew, I'd put my money on it and retire. What I do know is what's happened. And history is often a very good indicator as to where things are going. So I felt what a good idea would be to sort of look back to when I was in your situation, and then look at where we are now, and then take an equal leap forward and say, well, what does that tell you about the future? So what I'm going to talk about a little bit is who I am, because I'm not an academic, and although I've known Barry for many years, I've tended to sort of be involved in industrial and operations and not in academia, so I don't write papers and stuff like that. Talk a little about what the aim of the presentation is, and then talk a bit about what the world was like in 1978 when I graduated, what it's like now, and therefore what do we think 2050 is going to hold for you guys when you're standing here. Okay? So, who am I? God, sorry about the picture. My background is technical consulting, so I've worked for various technical consulting businesses, particularly around the Cambridge area, for the last 30 years. And in doing so, developed a wide range of products, mostly involving in some way or another a bit of power electronics. So that's everything from something that went in the back of a mobile phone to power converters in megawatt range, and a number of things in between. Currently, as Barry says, I fill a role as consultant director for Ricardo, who are one of the big automotive consultancies in the UK. And in doing that, I've been heavily involved in developing hybrids. Particularly, we did a big work for produced the first hybrid design for a Chinese organization. And also, way back in the early 90s, I was involved in a company called Wave Driver, which had a fully integrated, water-cooled, integrated drive, charger, and DC-DC converter in 1995. At least 20 years too early for the market. But we all learn from our mistakes. So that was when EVs were going to rule the world back in sort of 1995, and everybody thought California was going to introduce laws stopping anybody drive a car with an engine in it, and that EVs would sell like hotcakes. But here we are 20 odd years later, and has much changed? So anyway, that's my background. I work for a company called Ricardo. The charming chap on the left there with the moustache is Harry Ricardo. So he was a pioneering engine designer back at the beginning of the last century. He developed a lot of work in the early years on things like engines for the tanks in the First World War, but went on to develop a whole range of engine technologies. You may be familiar with the octane system, where when you buy your petrol, it tells you what octane it was. Harry Ricardo invented that. He also invented a number of key designs around combustion. So combustion was his key skill. And he developed an organization built around his patents. And very successfully was at it too. Move forward nearly 100 years, Ricardo's a very different sort of business. It's a large multinational engineering consultancy. At its heart is still engine design and transmission design, but we also do a whole range of other technologies that you would find in a modern vehicle, so electronics, software, things like that. So a few of the sort of things that the company does. It's developed, it was involved in the original four-wheel drive FFD, and this wonderful looking device here, that's the fastest diesel car in the world. So that's the world. We did that for JCB almost as a, well, do you think you can do this? And so the engine designers took two standard engines out of standard JCB diggers, modified them heavily, put them into that, and that thing did nearly 400 miles an hour. It was only limited by the wheels. It would have gone faster. They hadn't actually got the full power on the engines before they had to shut it down. The novel point about that was the way it was cooled, which was basically at the front, you shovel about half a ton of ice into the front of the car before you start a run. And it runs on, and basically uses that water as coolant. So by the time you get to the other end, you've basically boiled off all the water, and you have to stop. So not very sustainable, but a hell of a laugh. And also, we're never short of a cold drink. It was great. So other things done. This rather attractive-looking vehicle, that's called Foxhound. That replaces all the Land Rovers that were getting blown up in Afghanistan. So IADs were causing terrible damage to troops. The Land Rovers weren't designed to take it. This vehicle was designed from scratch. That's a completely new designed vehicle, taken into manufacture, and we made 300 of them within 3 years of the problem being identified. And they are now in Afghanistan, and well, they're slowly being pulled back, I guess, now. But they've all been delivered. So it does show if you take something out of the normal flow of development and actually put a team who know what they're doing on it, you can get something done quite quickly. And I think that harks back to what Bill was saying earlier about, you know, this is about innovation. It's about stepping outside of the norm and saying, well, what could we do if we just kind of threw away the rule book and had another go at it? So that was a completely new vehicle. It wasn't a modification. Every piece of that is fabricated from, you know, a clean sheet of paper. And so a number of other projects there, won't harp on. So that's what Ricardo does. It's a multidisciplinary consultancy, basically. And we do everything from engines through to developing software tools to make engines. The bit I work for is in here, and we get involved primarily, as you might suggest, in hybrid vehicles, electric vehicles, and all the systems that go with them. So this is nearly the end of the advert, so don't worry. Spread around the world, but it is a UK-based organisation. I think currently we have just over 2,000 staff, and we work primarily for the car makers, so all the OEMs, as we call them, and also some of the tier 1 suppliers, the big multinational suppliers. But that's what Ricardo does. And just as a, you know, because it's a great looking car, no other reason. That's the Bugatti Veyron, which is the fastest road car in the world. So when you see the Top Gear boys, you know, charging up and down the track with these monsters, there is a 7-speed dual clutch transmission in there. All of the electronics, all of the software, and the gearbox come out of Ricardo down in Leamington. So every one of those that goes on a road has a Ricardo gearbox in it. All of it developed and supplied by our company. And if it goes wrong, it's quite exciting because there's 1,000 Newton meters of torque going down through that gearbox. And you can imagine if that engine's going full power and you kind of miss a gear, it's quite unpleasant. So reliability, performance, these are the key requirements. So what do we do on hybrids? Well, it's an interesting thing that we tend to sort of think about hybrids, and everybody thinks about two things. They tend to think about electric machines, and they tend to think a bit about power electronics, and they also talk a lot about batteries. What they forget is all these other things. Yeah? So if you're going to design a hybrid vehicle, or in fact any vehicle, to be honest, I think we're moving into a culture where whether a vehicle is hybridized or not becomes less of an issue. It's more about what does it do and how does it, you know, what are the end results in terms of performance, miles per gallon, all these sort of things, and less about is it a hybrid. In future you won't care if it's a hybrid or not. You won't even know. But to get a good car, which is the point of the exercise, you have to do all of these things. You probably recognize all of them. Attribute attainment is a bit of an automotive engineering word. What it means is, what does the car feel like? So the attributes are, you know, drivability, NVH, noise, vibration, and harshness. Does it feel what you might call a good car? So if any of you experienced some of the early EVs, you will know what a good car isn't. Yeah? The problem about when people started making EVs was that they assumed by putting an electric motor in something with wheels on it and then, you know, going, look, it's an EV, it would somehow be a good car. And it wasn't. It was a terrible car. Most early EVs were awful. Their doors didn't shut properly. The windscreen wipers were rubbish. You know, all the attributes that you expect as a consumer of a car weren't there. The only thing that was there was the fact that it was electric. But everything else, you know, if you put a conventional engine in that car, no one would have bought it, you know, because it was a rubbish car. So making a hybrid or electric vehicle depends enormously on getting these other things right. not just, here's a big electric machine, here's a nice piece of power electronics, here's a battery, off you go. That doesn't work. And you will see over the years a number of attempts at hybridization by different car companies where they haven't got that bit right. So the technology's been okay, but what you've ended up with is a vehicle that doesn't feel or work as well as it should compared to its existing opposition. This is one of the big problems. Actually, a modern conventional car is a very, very good piece of engineering refined over 100 years. So you can't just come marching in with something else that's kind of a bit different technology, but actually rubbish at half the other things that it used to be good at. So when you're electrifying a vehicle, you've got to think very hard about all this other stuff and not just about, let's put a big motor, a big battery, and a piece of electronics in there, and it'll be great. So, what do I want to talk about today? Unsurprisingly, the world has changed a great deal. I think Bill already emphasized that. The slide rule is gone. I haven't actually seen one of those for years, Bill. I was very, very, very grateful for you to show me one. Things have changed a great deal. And I hope one of the things that will come out of this is just how much, and therefore how much you can expect in the next 36 years. Okay? So, as I say, it seemed interesting to contrast the roles of power electronics over the last 36 years and where we're going. So, you'll have gathered my background for the last few years has been in transportation, but that's not the only area I've worked in. So, it's got a transportation theme, but I might stray off that now and again. Okay, so, talking about vehicles. A few numbers. There's an awful lot of them. There's an awful lot of cars. 65 million cars made every year. 65 million. Yeah? And another 21 million commercial vehicles. Okay? So, if you're thinking about a production line, they're coming off faster than you can count them right now over the world. There's cars coming out everywhere. And all of them are a fairly complex and sophisticated piece of technology. So, if you think that you're going to put one of these in every one of those, you're talking about a big revolution, because there is nowhere that the industry is anywhere near capable of doing that. 65 million inverters, that would be the minimum you'd require. So this is a massive industry, and the numbers are mind-boggling. I know some of the challenges in, say, aerospace are very demanding, but, they make a few hundred, maybe a few thousand aircraft a year. 65 million cars. And potentially every one of those is going to have something done to it over the next 36 years, because right now most of them are in internal combustion engines. So as a comparison, we're talking about hybrid and electric vehicles. Last year in America, the biggest market for new technology vehicles, there was about 500,000 cars sold that were either hybrid or electric vehicle. About 50, 60,000 of them were actually EVs, all the rest were hybrids. 80% of them were Toyotas. So one company has a complete stranglehold over the entire industry in this area. It's hard to understand quite how far ahead they are in terms of market share. I struggle to find any other industry, even Microsoft, don't have such a dominant position in the market as Toyota do in hybrids and electric vehicles. So it's an enormous challenge to catch up with them. Make it very clear, you guys have got a long way to go. I don't know, some of you may work for Toyota, in which case you're looking very good. But it's a hell of a challenge. The rest of the automotive industry is just racing to try and even catch up. And of course, all the time, Toyota are marching ahead. So they really have revolutionized. It's hard to understand how much they've changed the landscape. And what they've demonstrated is you can do it if you get scale right. So they've already made 4 or 5, I think they've made the 5 millionth Prius has come out of a production line somewhere. So they've made 5 million. Everybody else is struggling to make 50,000. If anybody else sells 50,000 hybrids or electric cars, they're really quite pleased. So that they're a long march ahead of everybody else. And, we've talked briefly about passenger cars because the numbers are big, but don't forget there's all these other areas, commercial vehicles, off-highway vehicles, so diggers, excavators, all these things. and then the rail networks and marine. These are all transportation methods. They all use, to a large extent, all use internal combustion engines as their primary method of movement, and they all are going to be increasingly impacted by emissions controls. Okay, because that's what drives all of this, by the way, emissions controls. So let's have a little quick history lesson. So 1978. You've already seen a classic example of a 1978 vehicle earlier from Bill. So by and large, spark-ignited engines, your conventional gas engine is the dominant player. There's very, very limited electrification in the vehicle. Almost certainly has a manual gearbox. If you're really smooth, you might get one of these new 3-speed ATs that just about knock your head off every time the gearbox changes gear. And the only electronics is really in the ignition control system, maybe, if you're lucky. Most of them still have a distributor and a coil. Clicks round, knocks open a pair of contacts, the coil discharges, you get a spark. I know you're all looking going, what? Surely that doesn't work. Yeah, but it does actually. But that's how most ignition systems worked. The HMI, the human machine interface, it was basically a couple of lights and some cable-driven dials that told you how fast you were going. The alternator, that was quite sophisticated. That actually had a linear regulator in it and some diodes. Very exciting. And safety features, yeah, you could get out the doors. You know, that's about it. Seatbelts weren't even obligatory. Never mind, airbags hadn't yet been conceived. Certainly stability control was basically just how fast you could turn the wheel. So very, very little. And of course, virtually no emissions or fuel economy concerns. V8 engines, you know, you name it. As long as it ran, you didn't really care. The only problem was everybody realized that the amount of oil that you could possibly get might be limited by the fact that most of it wasn't here. So that was shortly after the original sort of big oil crisis. But, you know, fuel economy as a demand on the car makers was pretty non-existent. So where are we now? Well, a long way forward. Vaster range of different powertrains. Certainly in Europe, compression ignited engines, in other words diesels, very common, about 50-50 split between those and SI. Multi-speed automated transmissions are very, very common. So some of the high-end cars are now talking about 8 or even 9-speed automatic gearboxes. So 9 different combinations of operation, almost continual variation in gearing, as well as so-called dual clutch transmissions. We're not going to talk too much about transmissions, so don't worry. But point is, all of these are automated. The advantage of automation for you guys is that it allows you to get the use of an electrical machine far better because you've got a nice gearbox in the way, which you can control. So you can control the timing of the gear shifts if you're using a hybrid vehicle. Electric propulsion, we're obviously seeing quite a few different types of EV come out. Plug-in vehicles, they're still niche, but they're appearing. The main thing is the sheer intelligence within the car. You know, you've got 60 intelligent nodes in a high-end vehicle now. So, you know, 60 processors all whirling away doing different things. So really a quite complex system. Sophisticated user interface, you've got all your infotainment, all sorts of stuff going on there to distract the driver. And then, of course, in terms of safety, okay, we still see car crashes, but survivability of car crashes has improved enormously over the years. And a lot of that's down to airbags and also electronic stability control, things like that. And a lot of all these things, at their heart, have some power electronics going on. A lot of these systems all require some form of electrical control to make them work properly. So the car is now a very complex set of electrical drives, power electronics, drivers, and so forth. So a hell of a different place to what it was back then. Electronics controls virtually everything. You know, virtually every part of your operation in the vehicle is electronically controlled. So where will that take us in the next part? Well, we're doing a lot of work just now on what's called platooning. And you've probably seen Google with their autonomous vehicle. The likelihood by the time you guys are our age is you won't drive. You will travel in vehicles, but you won't drive anywhere. You will almost certainly be guided to your destination by a complex set of computers and routing systems. If you do drive, you will almost find it impossible to hit anything. The vehicle will stop you hitting things, basically. One of the big questions, and this is not really an engineering question, it's a sociological question, which is, will we actually end up needing personal mobility anyway? Will public transport become far more integrated into the world, and that we can quite easily get from A to B without having to get in our own car? And also, if we do in a vehicle, it's actually not really a vehicle anymore, it's just a place to work or a place to communicate from, because almost certainly much of your interaction will happen by a virtual presence. So we'll have this conference, there's no one actually sitting here, you're all at your desks in your university departments, and you can be playing Scrabble or whatever whilst listening to me rant on. So when I started writing this down, I thought, you're mad, Thornton, this is insanity over here. And then I thought back and thought, well, when I was here, did I think this would be here by now? And there's stuff on there that I had no idea, not in the slightest. I mean, I might have thought EVs would be a great idea, but some of the level of control and sophistication in a modern car is extraordinary. I don't know how you saw that. There was a program on the other night about Voyager. Voyager was launched just around here, I think. And for those who don't know, Voyager is the first man-made object to leave the solar system. So Voyager is now way out beyond the outer planets, and incredibly, we can still hear it. And but the engineering that was in that was at this level. Circuit boards that look as though they were put together by a sort of donkey with a soldering iron, but it worked. And the point is, if you look at that and then you compare it to sort of I don't know, Eurofighter or something like that. Here is it a modern piece of technology? It is light years ahead, literally. And so you have to kind of go, well, another 36 years, we could actually make a hell of an impact. We could be not requiring cars as they exist now, but we will still need to probably travel, but by means we put a very high dependence on collision avoidance and things like that. So fuels, that's always going to be a challenge as well, but the conclusion is that it will be predominantly electrical. Okay, you will still have internal combustion engines. We can't get rid of them that fast because we've had them for 100 and odd years, and they're kind of integrated into our society. But increasingly, they will become a thing in a box where very little comes in or out of it, and what does is very heavily controlled. And also, again, you probably all remember Back to the Future, where the guy comes back with the DeLorean and flips the top open and chucks a couple of banana skins in and shuts it and goes, well, that's it, I've refueled. It might not be quite at that level, but one would expect multi-fuel engines to be commonplace. They already exist. You can already run some large engines on multi-fuel. But the idea that the fuel system will figure out what it is it's burning and adjust its timing and ignition to suit. Yeah? So that seems quite reasonable. So a bit of humour for those who are of my generation, and just bafflement for the rest of you. So, what happened in 1978? Well, I left university and moved into the real world, and got a job, which is always exciting. And I worked on these fascinating things called cycloconverters. AC to AC frequency changes, if you're not familiar with them. So, there's no mobile phones, there's no PC, so I didn't have to do that bit at the beginning to tell you to turn them all off. And the Walkman, which is a very, very sophisticated piece of audio equipment, it's just been launched by Sony. And Tim Berners-Lee is sitting somewhere going, how do we get everybody to talk to each other? It would be a really good idea if we could do that. But he still hadn't sort of come up with the World Wide Web, so we just relied on talking to each other. So I think the university had one major computer, an IBM 360, sat in the bowels of the building, and you basically fed the thing paper tapes or cards, and you got back a bloody great big pile of paper which you poured through and realized that you missed a comma out in line 6, and everything after that was rubbish. So it was kind of sad. I do remember a very, very sad incident where I watched a PhD student struggling back up past Claremont Tower in Newcastle, and he had this great big tray full of punched cards, all of which were obviously in the right order, because if they weren't in the right order, the program meant nothing. So he had this big pile of cards, and he made the schoolboy error of walking up there on a windy day. And because of the nature of the towers, what happened was a very sort of wind vortexing effect. And he got sort of so far up, and suddenly his entire PhD literally just went up into the air. And this poor guy spent the next 2 hours running around this area trying to collect all the cards up, and then presumably trying to get them back in the right order. But it was quite sort of, well, we laughed a lot, didn't we? But I'm sure he passed his PhD eventually. So a well-known broadcast came onto Radio 4, The Hitchhiker's Guide to the Galaxy, and the lucky Louise Brown became the first ever test tube baby. So these are sort of, again, you know, that's how far we've come. You know, only then was the first human being was able to create it using in vitro fertilization. And then, note that number there. Ford had 23 plants in the UK in 1978. Unfortunately, most of them were shut most of the time because industrial relations were utterly disastrous, and people spent most of their time not working. And here's one for you budding house buyers. Inflation reached a 6-year low, having been at over 20% for a while, of 8.3%. Interest rates were around about 13%. So don't ever tell me you've got it hard, because this was a period of extremely volatile economic conditions. And the world population, around about 4.2 billion, so 3 billion less. So, you know, the predictions are we're going to get to about 9 or 10 by 2050. So you can imagine that the number of cars they all need is quite a big number. So where was it? Right, let's try a little experiment, bit of interaction. Wake you all up, come on. Right, everybody stand up. Everybody, all of you stand up. Right, if you're under 30, stay stood up. So all the old blokes, sit down. Anybody under 30, stay stood up, okay? Right, now, stay stood up if you've actually used a thyristor. Right, so anybody who's actually used a thyristor, stay standing up. If you've never used a thyristor,
Does an experiment come for
use your imagination. Has it anybody who's not used a thyristor? Okay, sit down. Okay, so you all know what a thyristor is. Okay, everybody down. I was just intrigued as to whether anybody actually used thyristors anymore, because you know, when I was in your place, wow, what a man. You know, thyristors were basically, that was it. It was like thyristors and some other stuff, which hadn't been invented yet. So by and large, virtually all of power electronics was based on thyristor technology. Okay? Phase angle control, force commutation. The problem was, you know, you ended up with cubicles like this, you know, just for a 20 kilowatt drive, you know, that you couldn't get off the ground if you tried. Most of the drives are DC based. Most motors are DC based still. AC drives are beginning to gain popularity, but you know, most of them are direct online start and just used as on mains, direct on mains. Virtually all control is analog electronics because digital control has hardly been invented yet. So here's the good old 6800 processor, which is sort of slightly bigger than a 50-watt point-to-load converter now. And yes, it had 128 bytes of RAM. Yeah? So you didn't take very long to fill its memory up, tell me. And we had about 2K of, I think it had about 2K of ROM. So, you know, you had to write programs, you had to write it in machine code. None of this C nonsense and all this sort of, you know, compilers and all this. You had to write directly in machine code because it was the only thing that would fit. But, so it gives you an idea where drives were at that point. So, the gate turn-off thyristor, just becoming into existence. Toshiba had just developed one, and a year later they would put one onto a train as a sort of experimental first. The IGBT, you know, the sort of workhorse of power electronics now, is yet to be invented. Never mind taken to production, it hasn't even been invented yet. GE have got it hidden away in some lab somewhere. The larger power switching thyristors, they don't exist. The bipolar junction transistor exists, but it has an HFE of about 1. So you basically have to come up with a gate driver that shoves about 150 amps into the gate just to get it to conduct 150 amps down through the collector emitter. So not a great deal, you know. It was basically just a voltage amplifier. It was very little else. But you could turn it on and off, which was novel compared to a thyristor. Power MOSFETs were around, but they were just beginning to sort of gain traction in terms of being able to use them for useful applications. So quite a different world. And then transport, the vast majority of power electronics is big industrial drives. There are some sort of applications in the railway systems, for things like cycloconverters and some big DC drives. But the main application in road vehicles is inevitably milk floats. And, you know, Britain leads the way in milk float technology. And in fact, where I used to work with Bill, across the road literally was a company called Sevcon, who were one of the main suppliers of DC choppers to milk float industry, because Smiths used to make the milk floats. But at one point, you know, one of those stupid statistics was the most electric vehicles in the world were in Britain, because we had all the milk floats. But that was about it, so not a great deal to play with. So where are we now? Well, it's a complicated world. We have huge amounts of problem with gases being produced from our activities in all forms. Our energy comes from a diverse sort of selection of resources, but political and international tensions often sort of cause trouble with that. As you've seen already, the population growth is pretty impressive. You know, 4.2 to about 7 billion, you know, heading towards 9 fairly soon, you would have thought. And all of these are competing for, you know, resource, and everybody wants to be at the top of the pile, basically. You've got an ever-increasing large chunk of the population who now can see what everybody else has got. This is one of the joys of the internet, whichever way you look at the word joy in that sentence. Everybody can see what everybody else has got. And most people tend to think, I'd like that over there. They don't go, well, I'm a subsistence farmer in an arid desert. I'm fine here. No, they kind of think, well, I quite like a car and a house and stuff like that. So the demands on the world resources are going to just keep going up. And that's not news, but it's sometimes worth thinking about the scale of the issue in front of you. Yeah, you know, it's sometimes quite useful just to plot a few things on a plot. I was talking to one of you out there earlier about when you're doing any project, it's always worth just getting out a piece of paper and putting on it. You think, well, where is the rest of the world in context to this? You know, how hard is what I'm about to do plan out? Yeah. So, you know, I did one recently on battery packs, and I just thought we had to design a new battery pack, and I thought, well, where are we against, you know, and I plotted on Nissan Leaf's battery pack and the Tesla and various other things, and then I stuck the dot on for hours, and I realized we were going to have to make the highest energy density batteries ever been produced, which was a bit of a challenge, but on the other side, we'd just done the highest power density one, so that wasn't too bad. But the point is, you need to know where you are. Otherwise, your design team wanders off into a corner and thinks, why is this so difficult? And you think, well, because you're effectively trying to boil the ocean or something. So, you know, figure out what it is you're trying to do before you launch into it. So here's a pretty picture, bit of an eyesight test. What it shows are the CO2 CO2 requirements per kilometre for engines. So this is what we live and breathe by, CO2 per kilometre driven. So whenever you're talking to automotive, they always talk about grams per kilometre. What they mean is the amount of CO2 per kilometre. Okay, so here's sort of the Europe and Japanese trend, bubbling down here. The Americans started way up there, as you would expect, but are making efforts to sort of try and mitigate things, and everybody else is somewhere in between. But what's interesting is, you know, even only, you know, 10 years, or less than 10 years ago, you know, basically it was awful, you know. And everybody's kind of taken the big pill and gone, actually, we're going to have to do something about this, aren't we? And they're all heading. And you can see everybody's heading somewhere down here, 2025. Now that just gets you to 2025. So 2050's way down here somewhere. Yeah? So logically it won't, because actually if you plot that for another 36 years, it passes through the zero axis somewhere, and that's going to be quite difficult. So CO2, yes, just now, that's what matters. Probably by 2025, it'll be replaced by life cycle CO2. In other words, the entire life of the vehicle, or whatever else it is you will be dealing with, is taken into account. So even if it's a washing machine or anything, it'll be total life cycle CO2. How much carbon did you create in getting from, literally making this thing to burying it back in the ground again? And where did you bury it, more importantly? So that will change. Well, the metric will change, but the drive to get to these points won't. And the point is, this is all legislation. Yeah? What you will find in industry is nothing happens unless somebody makes you do it. Yeah? So, left to its own devices, the car industry would appear somewhere, because it would sell V8 engines to everybody. So that's what's driving passenger car. But you can be pretty certain, and in fact in detail, there are equivalents coming in for commercial vehicles, for ships, pretty much anything that runs on fossil fuels will have CO2 and fuel economy targets attached to it, and of course emissions. This doesn't talk about emissions, in other words, the nitric and hydrogen carbons that come out of the engine. There are a whole bunch of other legislation which runs to telephone booths, trust me. So it's a very, the world is full of standards and requirements that drive design. Okay? This briefly just sort of shows how the world's changing in terms of who makes all the cars. You won't be surprised to notice that, basically it's going to be South America and China and India where the greatest growth is happening, and that's just over the next few years. You can extrapolate that for another 30 years, and you can imagine that this will have changed again. I suspect in 36 years' time, China will not be the only global economy growing fast. You may well find by then, Africa is an enormous powerhouse. South America, likewise. Who knows what the geopolitical landscape will look like. But the point is, there's an enormous population that's very rapidly wanting to catch up, and they all want things like cars. So, talk specifically about vehicles. Conventional powertrain already has quite a lot of power electronics in it. Even if you weren't bothered about trying to make the vehicle move by electrics, actually a conventional vehicle has a load of power electronics in it, up here. And some of that is very sophisticated. All of it is massively demanding in terms of its reliability and its cost. And once you get the hybrid powertrain, then you start introducing the need for energy storage, for DC-DC converters, waste heat recovery systems. Probably one of the biggest areas of growth will be in terms of recovering energy back out the engine. The problem with an engine is it's a very good heat generator and a pretty moderate torque generator. So it's not very good at producing torque, it's very good at producing heat. So, typical combustion engine will be 35 to 40% efficient. The rest of it all disappears out the exhaust pipe or into the coolant. So you've got to get it back again. And really, it's not just waste heat, it's waste energy. So for every kilo of petrol you shovel in, most of it disappears and doesn't get to the wheels. And you just have to do something about that. So electrification helps with that, doesn't solve the problem completely. And then clearly for a fully electric powertrain, because you don't have this handy little combustion engine that sits there running away all the time and pumps things around and moves things, then you've got to do it all electrically. Even things like the aircon, pumps, everything has to be electric because there isn't anything to drive it from the engine anymore. So there's where we are. There are probably anywhere between 5 and 20 models now in each of those slots, depending on which car maker you talk to and what they're trying to achieve. So micro hybrids right through mild, full. At this point, there's a transition here, very important one. At this point, the primary source of fuel stops being fossil fuel. Fossil fuel burnt on board. So from here on in, you can actually get electricity off the grid or from anywhere else you want it. Whereas up till here, all you're doing is burning fuel increasingly efficient. So a full hybrid doesn't actually plug into the grid. It just uses fuel a bit more efficiently than a conventional vehicle. But all of them are increasing their level of electrification and the number of bits on board. So we mentioned Toyota a little bit earlier, and the only reason I mention it is because they've demonstrated how you can do this kind of massive shift in a technology and a whole area of industry. In 1997, they developed the first Prius. And they realized, to their credit, that the rest of industry was not capable of delivering the supply of systems and components they needed to do the job. So they hummed and hawed for a few years, and then they went, okay, we'll have to do it ourselves. So they basically rebuilt the power electronics industry for their end use and developed technology. So, you know, I think 4 or 5 years ago, the Lexus 600H came out, which was a variant on the Prius technology, but in a much bigger car. That sported a power converter with 34 kVA per litre. Okay? So I see people going, ooh, 10 kVA, 20 kVA. Guys, we passed that. These guys passed that a decade ago. You really have to get going, you know? We need to be worrying about 100 kVA a litre, not 10s and 20s. It's, you know, they are so far ahead, it's scary. Against, you know, even other good suppliers in the industry, because they took the big pill. Make no mistake, Prius cost them over $1 billion, you know, just to design a car, at least $1 billion. But they took the big pill, and where are they now? They are the market leader. They have a total stranglehold. They are dominant in their marketplace, and they haven't been idle. You know, they've kept going. So they continue to develop their technologies, a range of things, not just the power electronics, but you know, the power electronics is one area where they have had a huge impact, and it's made it affordable. That's the point. Prius sells because it sells for a price that's affordable. Most of the other hybrids are put on the market for a price that's not affordable, so people don't buy them. It's kind of a chicken and egg, you know. So it's a really big challenge for the rest of the car makers to catch up and start producing hybrid vehicles at a price people will pay for them. And remember, whilst the car companies are mandated by legislation to achieve certain CO2 figures and fuel economy, we aren't. You know, we're the consumers. We don't have to buy them. You can go out and buy a V8 Mustang tomorrow. Nobody's going to stop you, you know. But, you know, they've got to make these cars sellable. So the point is, one of the key ways of that is to get the cost of the electrification down. And that's the big push just now. Now, currently, the Europeans are looking very hard at 48 volts. You know, you may go, 48? That's not very many. Sure, can't do much with 48. The point is, over the last decade, we've all figured out that actually, if you do it properly, you don't have to do very much. You just have to do it at the right time in the right place. So shoving a great 50 kilowatt drive in the bottom of the car, okay, it's going to make it go faster, it's going to make it more efficient, but you can't afford to do that because you can't sell a car that's got a 50 kilowatt drive in the bottom of it unless you're Toyota, because you can't make it for the price you need. So 48 volts is where most of the big OEMs in Europe, at least, are currently aiming to do mild hybridization. So getting, if you remember that curve, they're at about 130 grams-ish now, some of them, most of them. They need to get to 95 by the end of the decade. 48 volt technology under their entire fleet might just do it, okay? So big gamble, but it's big numbers. Remember, even in 2015, when the 2015 mandates kick in, the car companies are probably going to be still getting fined several $1 billion between them all because they'll have failed to get there in bigger numbers, which is not bad given that the original number was about $8 or $10 billion. So they saved themselves quite a lot of money by getting on with a bit of hybridization. And also increasingly what we're seeing here, which is quite exciting and fun, doesn't do anything for CO2 by the way, is hybridization as a performance enhancer. So those of you who watch these kind of things will have seen McLaren P1, LaFerrari, the Porsche Spider 918. All of these are the classical top-end performance cars, except they're even better now because they've hybridized them. So all those cars have got one or more electrical drives put into them just to make them go faster. So the P1, which I know very well, I actually sat in one, wasn't moving at the time, but I did actually sit in it. That's got a 600 horsepower engine and 135 kilowatt electric drive in it, okay? And that means you get to 60 miles an hour in about 2.4 seconds, which is quite quick on the A14. Don't quote me on that. We didn't do it on the A14, trust. But the point is, the car makers have woken up to the fact that hybridization isn't just about economy, it can be for performance as well, which sells. In fact, it's easier to sell performance than it is to sell economy, because people like fast, wowy things. They're not that bothered by a little slow economic car, but they are quite excited by something that sort of puts their eyeballs through the back of their heads. So at the far end, EVs, again, you know, I've been there, done there, had the t-shirt of EVs. 1995 were meant to be, you know, EV was meant to be on arriving. 20 years later, it's still not really here. The real problem is price, and particularly the price of the batteries, but also of everything. It's all electric. And all electric stuff's expensive compared to mechanical stuff, generally. Yeah? It's a real headache to get away with the cost. It's not we can't do it. You know, we could electrify every damn car in the world if cost wasn't an issue. But it is. So, unsurprisingly, you see some rather exciting bits of kit here. Chargers are now becoming a big issue on board. Energy storage. That is actually the McLaren P1 battery pack. We designed that, he says, quite, in Cambridge. So that was designed in Cambridge by a team I work with. Big traction inverters, lots of big motors, DC to DC converters. These are all key parts of any hybridization or electrification task. But the problem is, compared to a bog standard internal combustion engine, they are terrifyingly expensive. Yeah? It is just the biggest issue by far. So, you know, when you're designing one of these, there's a lot of stuff to worry about, as you've all probably gathered even from what you're doing in your PhDs. There's a lot of different constraints on your design and what you can develop. But, you know, coming from the sort of industrial and commercial world, you know, that one just dominates, and it will dominate the rest of your education and your working lives. The cost of these things is the thing that dictates whether or not it actually gets to market. And as a practicing engineer, one of the things you will want to achieve is something that makes it into production. Yeah? That you know, I think for some of the older guys here will nod, hopefully, is there's nothing more satisfying than seeing something you've designed being used. Whether it's a washing machine or, you know, a nuclear power station, doesn't really matter. The point is, when you see something you think, well, we did that, or I was part of the team that did that, or I actually did that myself, whatever, that's the buzz. That's what kind of makes it all worthwhile. So my point being is, this is the hard sum territory. This is the analysis, design, all these things. But this will come again and again and again and hit you on the head like a ton of bricks, because you can have the cleverest design you like, but basically once the accountants get at it, you know, somebody earlier was sort of saying these different people, groups, but you know, that's the one that drives everything. So typically on electrification, really just put this in to point out that, you know, by and large on vehicles and transportation, you know, power and voltage pretty much link you together, and voltage costs. You know, as you move up the voltage curve, the costs go rocketing up, and you know, 48 volts is attractive because the 48 volt standard doesn't exceed 60 volts, and if it doesn't exceed 60 volts, then clearances, isolation, all that stuff doesn't matter. same as a 12-volt vehicle. You know, you can stick your hands in there, you can, you know, doesn't matter. Once you pass that threshold, everything changes. You've got insulation to worry about, safety, all these things. And as you go up this curve, it gets worse and worse and worse. You know, and Toyota and the other players have done a great job of making hybrid electric vehicles safe, but it adds cost at every point in the design cycle. So that's why 48 volts is so attractive. But you know, as you go up, you can get up bigger numbers, you can go faster, yeah. But the challenge is between functionality and cost. You know, how do I get these features without shoving in a load of cost into the design? So I think this picture's already been used. It's just come out recently. But I was just saying about Toyota, that's already galactically good in comparison to most of the people's attempts to. Bear in mind that's 2 inverters in there and an up converter. So that's a boost converter and 2 inverters in something about this big that will power a large vehicle. So that's running, I think that one runs about sort of 20 kVA a litre, something like that. And now they've basically gone, let's get it down by a factor of 5. Let's not mess around. A factor of 5. This is literally a shoebox to power a car, you know? So are they a long way ahead? Oh, yes. You know? So if you're thinking about where to set your goals, where to set your points, you're going to have to be quite ambitious because that's a hell of a leap. And whilst that's not production, I mean, everybody suddenly goes, oh, Toyota can do silicon carbide, they're going to put in car. No, they're not. You know, it's a way off because that will cost them about 8 times that one does. Yeah? So the cost is still the prohibitor here, not the technology. But, you know, as it says there, you know, the 600H did that 3 or 4 years ago at least. And the German activity, Motorbrain is an output of, I think it's Siemens, Infineon, Fraunhofer Institute, and one of the other big OEMs, big tier ones. But basically, this is a fully integrated machine drive system. And by that, it means it includes the gearbox as well. So that is a high-speed machine with an integrated transmission in it to bring down to sort of road speeds, wheel speeds. You know, so typically a car wheel will do maybe 1,000, maybe 1,500 RPM max. So whatever you do at machine level, you've got to get down to road speed level eventually somewhere. And that's one of the big problems about cars. You know, you can't run the car wheels at 15,000 RPM. Well, you could. They'd have to be about this big. It'd be a kind of weird car. But that's the point. You've got this challenge of getting from what's efficient for electrical systems, which is lots of lights, high speed, you know, get the speed up, get the size down. But then the real world wants you to run on tires and stuff. So that sort of, you know, so all the gains you make in moving the size up, moving the frequency up and the size, you know, if you've got a rubbish gearbox, it just comes back out the other way. You lose it all going the other way. So overall, system thinking is another big issue. Think system, don't think component. Think system, then design the component. Yeah? And then these are some more examples. So this is, I think that's out of the Leaf. That's the Mitsubishi machine out of the Miev, I think. And I think that's another power converter. But you see a number of features, which is interconnect is always a challenge, you know? Connecting things together is a pain in the backside, particularly when it's in a vehicle. If you can eradicate connectors and cables, you're doing a good job because they are expensive, they fail, they get broken. Generally, they're not something you can control within the product design so well. So avoid connectors if you can, and that's why integration is so important. People kind of think of integration as just making it smaller. Really, integration is about removing components out of the system so you don't have to pay for them and increasing reliability, yeah? Not just making it smaller. Because often making it smaller is not essential. It's just making it more reliable that's important. So we talk a lot about wide band gap, but also passive component development is pretty as important, if not more important than these. In many ways, the power semiconductors are kind of leaping away ahead again. So they're going, hey, look at all these things we can do. I can switch at 100 kilohertz and no loss and all this good stuff. And then you go, yeah, and here's the inductor, here's the capacitors, you've got a packaging problem, you've got a thermal problem. The capacitors don't like to be 105 degrees, it's too hot, don't work anymore, all this kind of stuff. So the power electronics is kind of surging away, going 250 degrees, yes, that'd be great. And then the passive components are going, no, we can't work in that, it's far too hot for us. So there's probably more work to be done on passive components than there is on the switches in many ways, because they're not the size limiter. The passive components are the size limiter. So these are some figures put out by the DOE. I'm not sure whose book they've been reading before they put them up there, which you'll notice, apart from anything, is we can already do that. We can already do that. Actually, that's not a challenge. What is a challenge is that. So if you do a few sums, yeah, $30 a kilowatt, okay? So if you want a 10 kilowatt drive, they only want to pay $300 for it. Now, if you go and look on your RS catalogue for a 10 kilowatt drive, it will cost you a hell of a lot more than that. I don't know, Bill might have a number he can sort of spit out, but I mean, industrial drives are probably 8 times that, 5 to 8 times that at least, in terms of cost. The US want it down to $8 a kilowatt. And that's the drive. This is not just the electronics or the motor. So, they want to be able to make a, 50 kilowatt drive. So that's all the electronics and the motor manufactured to high performance production for $400, 280 pounds. You couldn't even buy the bits, even if you tried, in volume just now. So that's not difficult. That's not particularly difficult. That's relatively achievable with silicon carbide. That's the killer, right? So I think they actually got this slide wrong. Those numbers just aren't challenging enough, because you can do better than that, and still, you have to do better than that to achieve that, because you can't afford to put that much material in the box. You can't buy that much kilograms of metal, silicon, plastic, and everything else at $8 a kilowatt. You pretty can't buy the raw material. So a huge amount of work to go on, but most car manufacturers would be delighted if they could do that now. They're struggling. It's nearer 50 at least. Okay, this eye test is just to show you what the impact of how we drive has on how you design a car. So, Barry, I notice I'm going over time. Am I all right chugging on for a few minutes?
5 more minutes.
Okay, keep awake, boys. It's not long. It's not long to go now. The pain will go away, don't worry. So these are just different drive cycles. So the NEDC is the test cycle that all of Europe uses to develop their cars. The main problem is nobody in their right mind drives like this. In fact, nobody physically can drive like this. These are test cycles, and they have about as much to do with the real world as that a noddy does. They're very different. And the problem is, if you designed a car to do the NEDC, you'd actually realize that you could actually do quite well with a 6 kilowatt motor. Yeah? So you could actually drive the NEDC on a normal sized car with a 6 kilowatt drive. Not a bad deal. How many people would buy that then? Because it's a stupid drive cycle that nobody ever drives. Nobody drives like that. So if you sort of put some of the more complex ones in, you start getting much more sensible numbers. You get up to 50, 60, 70 kilowatts. Still, you find that if you take something like a BMW 5 Series, it will peak out at around 160 kilowatts. Yeah? That's what it can do. How often do you use 160 kilowatts? Unless you're a racing driver, virtually never. So we design these vehicles with massive short-term power capability and then optimize them for that power delivery. So you optimize the engine for best fuel economy up or near its maximum power point. But we don't drive there most of the time. You drive down here. Going along the motorway at 70 miles an hour, you're still only using about 10, 15 kilowatts. And yet, so the engine's kind of sitting down the bottom left-hand corner of its efficiency map. So it's running inefficiently when it should be running as efficient as it can be, because that's the thing you're doing most of the time. You know, it doesn't matter about the efficiency during acceleration because you don't accelerate for very long. What matters is the efficiency when you're in steady state. So we've kind of got the whole car design thing a bit backwards. And that's one of the things that over the next 30 years you're going to have to actually unravel and get back the right way around, which is you want a steady state power plant that's incredibly efficient at relatively low powers, but can go to 5 or 8 times overload for short periods of time without braking. So that's the challenge. And here's a completely different part of transport technology, which is that currently the vast majority of the world uses spark ignition, you know, good old spark plugs in the top of your engine. Some of the work we're doing recently is on what's called corona ignition. So this is using a corona gas breakdown that effectively ignites all the gas in the engine simultaneously. So instead of having a spark propagates out, the corona ignition ignites the whole lot in one go. And this produces a much better burn of the fuel. And though, unsurprisingly, you get better emissions, you get smoother operation, longer life, blah, blah, blah. However, currently, even our best attempt at a corona ignition system is, you know, this big. But let me take you back to 1978, when ignition systems were basically a coil and a contact, yeah? And where we are now, so how long before we get to a point where you can have a corona ignition system in something that big, yeah? That's your next job, so write that down. Things to do next week. Okay, very briefly, the world of hybrids is coming to big vehicles as well. Actually, they're quite good at it because they do all sorts of weird repetition cycles that electricity quite likes. So a whole bunch of activity in the off-highway sector. Trains, unsurprisingly. Again, probably one of the early applications for wide bandgap devices because they can stand the cost. These are bigger systems, lower numbers, higher value, much longer life. You know, you want to think on a train that lasts 25 years at least. But again, a lot of work going on by particularly the Japanese to introduce silicon carbide into rolling stock. 36% of the size of its predecessor. So that's pretty impressive. And ships go to the extreme. You know, big multi-megawatt drive systems. Most people now are moving to so-called azipods, you know, electric drives under the ship. High maneuverability, high performance. And also, almost certainly America, within the next few years, will introduce anti-idling laws for their harbors. So you can't bring a ship into a harbor with the engines still going. You'll have to shut the engines down and bring it in electric mode only, or some other way. Guy in a rowing boat, possibly. But, you know, this all-electric mode for a ship. Again, you know, same sort of architectures in the cars, but much, much bigger bits. So, again, more parts to play with. So, what have been the key improvements over the last 36 years? These are just some that sort of came to mind when I was thinking about this a little bit. But I think, without going through them all in detail, I think what you recognize is that all of these have made a huge strides forward. But out of all of them, actually, this is one of the most significant. Our ability to do very, very intensive, complex, real-time calculations and spit the answers out, and therefore allow us to control things in ways we never dreamt were possible before. So control of the whole thing, whether it be the machine, the power electronics, the system, whatever, comes to being the key to the magic box. So as these things progress, because you've got this control, because things like digital telephony have revolutionized the amount of technology in terms of computing you can get in a small space for very little cost. You know, the mobile telephony business has driven the volumes in this kind of embedded control technology so fast that it's now way ahead of what this can do. So your opportunity is to use all this stuff to make this do what you really wanted to do in the first place. So biggest challenge is cost, by far, okay? You know, you get standardized components, you get a supply chain, you go back to cost. And that loop, that's That's the way the world works, yeah? And in that you sit with your power electronics and drives, and you have to get it to work for you, for your application, you know? That's how the world runs. So, 2050. So we've talked about now, we're in early hybridization, beginning to see niche EVs, so forth. 2025, we expect to see advanced 48-volt systems, downsized engines, 2-3 cylinder engines, lots of turbocharging, superchargers, those kind of things. A lot of weight reduction, aluminium chassis, generally getting rid of bits of metal you don't need, much more sophisticated understanding of what happens in crash, and therefore, you know, you can chuck out bits that you don't need, you only keep the bits that you need in the structure, and so on. Lots of things going there. And then long term, you know, yes, electrification will be dominant. However, the internal combustion engine will still be there. We cannot do without it in that period of time. But it will be very much designed to be much lower weight. It will be boxed in. It will be heavily constrained. It will be silent. It will be very low emissions, and it'll be very, very efficient. But it will still probably be there because dragging, you know, it's still a way of converting an easily transportable fuel into work. So, power electronics in 1978, pretty much non-existent in transport. Now, it's everywhere. You know, IGBTs, MOSFETs, you know, bread and butter stuff. We're just at that threshold of wide band gap being the next big thing. So here, we had thyristors, and people talked about these things. You know, gate control devices. Wow, that sounds good. Can we have some? And you guys are already here going, silicon, that's okay. Wide band gap, that sounds good. So, you know, I'm expecting you to get as far from here to here in the next leap, at least. And if you don't, I'll send my son around to see you. So, I said, as a new undocumented devices, I don't know what's going to happen. These guys around here might. You know, Phil Moore may have something up his sleeve. Who knows? But the point is, there will be some new devices coming along which you will get to play with. Computational power will permit you to do all sorts of clever things that even now we're kind of struggling to conceive of. So that's the point, coming back to earlier speakers, is think big. You know, what could you do? You know, I'm looking forward to seeing the, you know, the interstellar drive or whatever it is going to be. But, you know, this is where you need to be, at least, I would have thought. However, remember, most of the semiconductors are still in the hands of a few very large organizations. With a few exceptions, the big organizations will always hoover things up. So, GaN Systems, a wonderful organization, doing a great job, but if they're successful, they will get eaten up by someone. In fact, they'll probably want to sell to somebody. But the point is, it's very unlikely that in 20 years' time, an organization like GaN Systems will still exist as GaN Systems. You might object to that.
We don't do it. We don't make the semiconductors.
Yeah. You're a design.
The semiconductor company in the world
Yeah.
makes them.
Yeah.
We just figured out
How to make them. Yeah. But the point being is that will be the model that continues. There will still be the Infineons of this world, and they will dominate the supply chain of these components, which dictates to some extent the cost. So you are constrained by that. And undoubtedly, some power electronics will become commodity. You know, inverters will become a commodity item, certainly in the automotive world. But my suspicion is that the three-phase, two-level inverter will still be around, despite all our attempts. It was perfectly good here. It's still good now. It'll probably be still good for another 36 years. So I'm going to skip through these because we kind of covered them earlier. This is all about sort of the way the utilities will probably get much more involved in the whole side of transportation, because they own the power source now. So suddenly it's moved from being the petrochemical companies to being the energy suppliers. And the energy distributors, they will have much more control over, you know, what goes into your car than BP does, for example. And I think the whole sort of area of the interconnected and grid-connected vehicles, is yet to really work. I think people have talked a lot about it. We've been messing around with it for 20 years. You know, you've got contactless, you know, wireless charging, you've got high rate charging, all these different things, fuel cells, all these. Which one's going to win? I have no idea. But it's up to you guys to sort of try and put them out there and let people find out what works for them. So, what drives the world? Some of these sort of fairly enormous things, you know. We live in a very complex and ever more connected world. And, you know, electrical energy the applications for electrical energy will grow, and therefore the applications for controlling electrical energy will grow. But in a free market, economics dictates what happens. Whatever you like to think, whatever creed, religion, or whatever, economics drives the world. It may not be what you want to hear, but it is. And therefore, you will always be concerned by cost. So the closing point I would make is that where you actually get to in the next 36 years is genuinely only bounded by your imaginations and your drive and determination to make these things happen. There are constraints, and you will always have to work within a set of constraints, with economic cost being one of them. But the main thing is that you've got a fantastic set of tools, devices, resources to allow you to do that. So my challenge to you is make it happen. Okay? Thank you very much.